Ever wondered how a car lifts itself at the garage, or why divers must be careful when surfacing? The science behind this everyday phenomenon lies in two simple but powerful fluid principles, which is Pascal's law and Boyle's law. For Pascal's law, pressure applied to a confined fluid is transmitted equally in all directions. The real-world application is like hydraulic car lift and brakes, excavator and cranes, manufacturing presses. For Pascal's law, pressure applied to a confined fluid is transmitted equally in all directions. The real-world application is like hydraulic car lift and brakes, excavator and cranes, manufacturing presses, which is for shaping metal, molding plastic. For Boyle's law, for a fixed amount of gas at constant temperature, pressure and volume are inversely related. The real-world application is scuba diving, which we are breathing a compressed air. When we are ascending too fast, it can cause the bends. Together, these laws form the foundation of hydraulic system, pneumatic tool, medical devices, and diving science. From heavy industry to life-saving technology, fluids in action shape our world. Let's dive deeper into the science and engineering behind these powerful fluid principles.
This experiment is to demonstrate that a liquid disconnected containers will reach the same level regardless of the container shapes due to the pressure being transmitted equally, which is Pascal's principle. So, materials needed is straw, 3 plastic bottles, hot glue gun, scissors, waters, and food coloring. So first, drill a soldering iron to make holes and insert the straw into the hole in the bottle and secure it using a hot glue gun. And let's do the experiment.
The first situation is that the bottle in the middle is closed and the bottle on the both sides is open. Pour all the water into the bottle. The result is that the water level in the closed bottle is lower, while the left and right sides are at the same level. The second situation is the left and middle closed while the right bottle is open. Where two bottles are closed and the water is poured into another bottle that is not closed, remove the cap bottle one by one. The result is all 3 bottles have the same water level. The third condition is left and the right bottle closed while the middle bottle are left open. Pour all the water into the middle bottle. Remove the cap bottle one by one. The result is all the 3 bottles have the same water level.
Okay guys, let's jump to the calculation. In condition 1, the middle cap is closed while the left and right caps are open. Water is poured into the right cap and the water levels are measured. From the experiment, the measured heights are 0.072 meters, 0.027 meters and 0.072 meters. As we know, the fluid density is rho equals to 1000 km per meter cube and the gravitational acceleration is 9.81 ms square. The pressure at the left and right caps is calculated as PL equals to PR, which is rho GHL, and you get 706.32 pascals. And the pressure at the middle cap is PC equals to rho GHC, and you get 264.87 pascals. Atmospheric pressure is taken as a standard value 101,325 pascals. And the final pressure acting on the trapped air is pressure 2, which is atmospheric pressure plus with the first pressure, and you get 102,031.32 pascals. Applying Boyle's law, V2 over V1 equals to P1 over P2. When you calculate it, you will get 0.993. This shows a small decrease in air volume due to the increase in pressure. In condition 2, the right cap is open while the middle and left caps are closed, and water is poured into the right cap. After pouring, the middle and left caps are opened, and the final water height are recorded. Measured height are 0.054 meters, 0.056 meters, and 0.05 meters. Pressure at the left and right caps are 529.74 pascals, and the middle cap is 549.36 pascals, which is initial pressure, and final pressures are 101,854.74 pascals. Applying Boyle's law, you will get 0.995. In condition 3, only the middle cap is open while the left and right caps are closed and water is poured into the middle cap. After that, the left and right caps are open. The final measurement heights are similar to condition 2.
In this experiment, we tested Pascal's law using a 3-bottle hydraulic system under 3 conditions. Condition 1, fully sealed system. Liquid levels did not equalize because trapped air compressed under a pressure, preventing uniform liquid rise. This shows Pascal's law transmit pressure but air bubbles break level equilibrium. For condition 2 and 3, 1 bottle open. Liquid levels equalize because atmospheric pressure took over, allowing the system to reach hydrostatic balance, not confined pressure transmission. The key takeaway here is the Pascal's law works perfectly only in a fully liquid filled, air-free sealed systems. In real-world hydraulics like brakes or lift,
Bleeding air is essential for smooth and predictable operation. This experiment clearly shows both the power and the practical limits of hydraulic force transmission.